Yes, thank you very much for the invitation and the introduction, Takayoshi. And I hope everyone can hear me and see my screen. I'd also like to thank the organizers for doing such a wonderful job communicating all this unusual format for a conference. So the work I'm going to talk about today is joint work with Jay Roberts and Steve Scholler. So I'm going to be talking about affine motion of 2D incompressible fluid flow in both the case of perfect fluids and also magnetically conducting fluids. And I'm going to break a few rules for the session here because this problem I'm going to consider in the affine geometry, which will reduce the problem from PDE to ODEs. And actually, there's no dissipation. So what we're going to find is a completely integrable Hamiltonian system. So, but at least it has something to do with PDEs and fluids. And what we'll see in this case is quite different behavior for fluids versus MHD. So here's the outline of my talk. I'll start with the discussion of the free boundary problem in general, and then we'll specialize to the case of affine motion and work out what the initial value problem looks like in this case. And then I'll show how this is reduced to a phase plane problem, which is fairly easy to analyze. And then we can use that to understand what the long time behavior is of the solutions in the case of affine motion. So let's begin with the PDE problem. So the basic equations are here. They have the equations for conservation of momentum, Faraday's law for the magnetic field, incompressibility, and Gauss's law for the magnetic field. So the notation is U stands for the fluid velocity vector field, and we're in 2 dimensions here. So this is taking values in R2. dt is the material time derivative. B is the magnetic field. The case where B is identically 0 reduces the problem to the incompressible Euler equations. P is the total pressure scalar. And we're going to be interested in solving this in a space-time region, C sub t, which we'll now discuss in more detail. So we're going to solve the PDEs in a region of the form where t is in some time interval, and at each time x belongs to some fluid domain omega sub t. And this domain is changing with time. So what we have here is a free boundary problem. We'll have initial conditions given on the time 0, so the initial fluid domain omega 0. And then we need boundary conditions on the lateral boundary of the space-time domain C sub t. So this is when x is on the boundary of omega t and t ranges throughout the interval. And in order to describe the boundary conditions, let's denote the normal, the space-time normal along the boundary by eta. So there are several conditions that we have to satisfy. The first is that the space-time velocity vector is tangent along the lateral boundary. And this simply says that the fluid particles remain on the boundary as the fluid moves. The pressure should vanish on the boundary. This expresses the fact that the fluid is surrounded by a vacuum. And we want the magnetic field vector to be parallel to the boundary of omega t at each time. So these are the boundary conditions that we impose. Now, for the PDE problem, we have local well-posedness with an additional condition, which is usually referred to as the physical vacuum boundary condition. It says that the normal derivative of the pressure should be strictly negative on the boundary. And under this assumption, there's a rather large, significant body of work which establishes the local well-posedness of the initial value problem in the case of perfect fluids by a number of authors. And more recently, there's been this analogous work in the case of MHD. So all of these works impose this physical vacuum boundary condition. But for what I'm going to say today, this condition will not be necessary. All right, so now let's consider the special case of affine motion. So first of all, let me explain what I mean by a motion. It's a one parameter family of orientation preserving deformations of some reference domain, which we'll take to be the unit ball. And so we simply get this family of deformations by solving this ODE using the velocity vector field U. So this we could think of as describing the trajectories of the particles. All right, so if we consider the image of the reference domain under this motion at a particular time, that gives us the configuration of the fluid at that time, the actual domain occupied by the fluid. And here we have incompressible motion. So that's characterized either by the fact that the divergence of the velocity vector is 0, or equivalently the gradient of the deformation has determined it equal to 1 for everywhere. And under this condition, the motion is volume preserving. So in particular, the measure of the fluid domain is preserved under the motion. All right, so now let me explain what I mean by affine motion. It's the special, very simple case where the motion is given is a linear function of the material coordinate y. And so in particular, this says that the deformation gradient is a function, a matrix valued function of time only. So here, this is the actual quantity that we're going to be interested in. It's this matrix value, 2 by 2 matrix valued function A. Since we're going to be working in this space of 2 by 2 matrices, it's necessary to give put some norm and inner product there. And it's convenient to take the Euclidean norm. So, or sometimes this is a particular norm is called the Hilbert-Schmidt norm, but it's really equivalent to the Euclidean norm if we identify the 2 by 2 matrices with R4. Okay, so for incompressible motion, we want the determinant of the deformation gradient to be equal to 1. So therefore, we want our solution to take values in the special linear group. So this is going to play an important role for us. Now, in the case of affine motion, the fluid domains are the image of the ball under the under the matrix A of t. And so these are, of course, very simple, turn out to be a one parameter family of ellipses with fixed measure since we're incompressible. And the dimensions of these ellipses are determined by the eigenvalues and eigenvalues of the stress tensor. And so in particular, the diameter of the fluid domain is proportional to the largest eigenvalue of the stress tensor, which, because of the way we've defined the norm, is essentially the norm of the deformation gradient. So, of course, we can talk about affine motion, but it's not, of course, necessarily true that given PDE will have affine solutions. It does, however, turn out to be possible to find solutions of the initial value problem with this special structure. So that's what this slide is about. If we take a time interval, I, and suppose that we've got a curve, A of t, defined on I, which takes values in SL2. We have a scalar function and finally a non-negative constant kappa, which satisfies this, this ODE. So assuming that we have this, then we can obtain a solution of our problem by making the following definitions. So the fluid domain will be the image under A of the unit ball. And then we define the velocity and magnetic field vectors as I've shown here, and also the pressure. So I don't have time to explain where this comes from, but it's basically an exercise in calculation based on assuming we have an affine motion and substituting into the PDEs, and it turns out that these definitions are essentially necessary. So if we make these definitions, then the triple U, B, and P solves the MHD system that we talked about in the space-time cylinder, which associated to these fluid domains omega t. And the important thing is that we also satisfy the boundary conditions. Notice that the sign of the pressure is given by the sign of the scalar function lambda, because the term here is non-negative in when x is in the fluid domain. So we'll come back to that point later on. And also notice that when kappa is 0, then the magnetic field is 0, and so then the problem reduces to the Euler equations. All right, so a few words about SL2. So again, these are the matrices, the 2x2 matrices with determinant 1. And we're going to regard this as a three-dimensional submanifold embedded in M2, our space of matrices. Now, the normal to this manifold is given by the derivative of the constraining function. Obviously, I'm supposed to keep an eye on the chat. So the question was, can P be 0? And the answer to that is yes. As we'll see, either P is non-zero everywhere except on the boundary, or it can be identically 0, and it can be negative. All right, so the normal vector in this case is represented by the cofactor matrix of A if we're at a point A on the manifold. So then the tangent space is a set of vectors which are orthogonal to cofactor matrix. This defines the tangent space at a point. And the natural phase space for our problem is the tangent bundle. So the set of pairs A and B, where A is has determinant 1 and B is in the tangent space at A. So if we have a curve with values in SL2, then its derivative will be a tangent vector. And so therefore the pair A prime will generate a curve in the phase space. So in this sense, the tangent bundle is the sort of natural phase space for our problem. Now we can give our equations a Lagrangian formulation by essentially taking a constrained harmonic oscillator, which I've done here. And the main equation here is given by equation 1 here. And this should be solved with the constraint that A has determinant 1. And now the important fact is that if we have a function, matrix valued function, which satisfies this equation, then it takes values in SL2 if and only if the pair A prime is in the phase space at some time d, and the Lagrange multiplier lambda is given by this expression in terms of A and its derivative A dot. So this therefore tells us that gives us a formulation of our ordinary differential equation as a nonlinear system of ODEs. Yes, A is non-singular because it's going to take values in SL2, so its determinant is always equal to 1. So it turns out that the initial value problem for this system, this ODE system, has a unique global solution. And so therefore, we get correspondingly a global solution of the PDE problem in the special case of the affine motion. So this is a 6-dimensional problem because that's the dimension of the phase space. And I would point out that in the case of perfect fluids, when kappa is equal to 0, this equation is nothing more than a geodesic flow in the special linear group with the metric induced by the norm that we've selected. And this is because in this case, the acceleration vector is in the direction of the normal to the surface. Now, this system has 3 conserved quantities, which can be expressed by these functions that I've defined here. So these are functions defined on the phase space. And if we have a solution to the system 2, then along the solution curve, these quantities are conserved. So in particular, the first invariant is which is essentially the energy of the system, gives us the global existence result, because this tells us, for example, that the derivative of A is bounded. The other 2 invariants correspond roughly to the invariance of the problem under left and right multiplication by rotation matrices. All right, so this come back to the question of the sign of the pressure. The Lagrange multiplier that we talked about a few minutes ago, this nonlinear function, satisfies an identity here where the x's here are the invariants that we defined a moment ago. So these are the functions of a and b from the previous screen. This is a general identity. But if we have a solution of our problem, then we see that the sign of the pressure is determined by the sign of this expression here, which is conserved since the xi's are invariant. So we can therefore say that the pressure, we know what the sign of the pressure will be. So it's either strictly positive or strictly negative or identically zero. So there's no other possibility in this simple situation. All right, a couple of remarks. There's a classical study of the rigid body motion, which goes back to Euler, and the sort of more modern interpretation of this problem is to study geodesic flow on left invariant Lie groups. This is different from what we're doing here because the special linear group with the metric that we've selected is not left invariant. So this is a different situation. There's also a similarity with the classic result of Arnold, which showed that we can regard the solutions of the incompressible Euler equations as geodesic flow in the space of volume preserving diffeomorphism. So there's a similarity there. All right, now let's see how we can reduce this problem to the phase space. So I'm going to simply summarize the steps here. I don't have time to go into the details. So the first step is to introduce a set of coordinates for SL2, and once we have this, we can use that to provide a Lagrangian formulation in these coordinates. So that allows us to impose the constraint automatically. And once we have the Lagrangian formulation, it's automatic then to transform to a Hamiltonian system using Legendre transformation. And because of the conserved quantities that we talked about, this Hamiltonian system is completely integrable. Then we do further transformation to simplify the problem somewhat. And this is two different these are two different transformations depending on the sign, on whether the quantity x2 is non-zero or not. I'm not sure what you mean by these being symplectomorphic. Perhaps we can come back to that question at the end. So once we've got the correct Hamiltonian formulation, then it's rather straightforward to do a phase plane analysis. And then finally, we can reconstruct our solution A and then interpret the solution in various cases. All right, so a very important role in all of this is played by the rotation group. And this has there are a number of different ways that we can characterize the rotation group. So here, of course, is just a standard one parameter family of rotations. You can also think of it as the set of elements of SL2 which are equal to its cofactor matrix. So A is, in other words, is the normal direction at A if it belongs to SO2. Another characterization is that elements of SO2 are norm minimizers in the special linear group. So if we take the minimum of the infimum of 1/2 norm squared over elements of SL2, that's equal to 1. And the rotations are precisely those elements which achieve the minimum. And finally, another characterization is A is a rotation if and only if it's in the special linear group, and the invariant x2 vanishes for all tangent vectors B. And so this is the reason why we have two different cases to consider when we reduce to Hamiltonian form. All right, so here is the last step, which is the reconstruction formula. And I have to explain a little bit more after the slide what I'm talking about. But the basic idea is what we'll see is that all solutions of our ODE system have a factorization where of this form, where V plus minus are rotations. Remember, capital U here is just our one parameter family of rotation matrices. And S is a positive definite symmetric matrix. And these functions QI are going to be obtained by solving our Hamiltonian system, which we'll talk about in just a minute. So we can see from this, let's see, question. No, it cannot. What we can see from this factorization is that if we start with a material point, the first factor simply rotates the material domain, and then S is a deformation. We'll take that to an ellipse. And then finally, we have a rotation of that ellipse. And the principal axes of the ellipse are going to correspond to the eigenvalues of the matrix S. So here's a schematic of our motion. So we start with our reference domain B and perform a rotation. The red dot simply indicates a representative particle. Then the S deforms the ball to an ellipse in general. And then finally, we have the second spatial rotation. Now, of course, this is a snapshot at a fixed time. And so as we evolve in time, this picture will be changing. The shape of the ellipse can change, and of course the configuration will rotate. But since the motion is incompressible, the volume or the measure of omega t is always fixed. All right, so let's see. Here is the Hamiltonian system. So the object of interest for us really are the functions QI, but we have to consider the full six-dimensional system with the generalized momenta PI as well. And notice here that two of the generalized momenta P2 and P3 are conserved, and those correspond exactly to the second two invariants. The third invariant, or the first invariant, is the energy, which is nothing more than the Hamiltonian for this system, which I have not written down. And an important observation here is that as we if you look back at the reconstruction formula, the solution A will be a rotation if and only if the matrix S is the identity, which corresponds to Q1 equal to 0. And so, as we've noted before, that this can happen only if the invariant x2 is 0. So therefore, we have these two terms in our system here. Q1 can vanish only if we pass through SO2, but if that can only happen when the invariant P2 is 0. So basically, in that case, we simply delete these terms from the system. So there's never any question of a singularity in analyzing the system. All right, so here are the phase diagrams first in the case of MHD when kappa is positive. So we have the two cases where the second invariant first is non-zero. And here we see closed orbits. This is a portion, probably can't see the labels here, but anyway, this is 0. This is Q1 equal to 0. So here the solutions have Q1 strictly positive. The other two pictures correspond to the case when the second invariant vanishes, and then Q1 is allowed to vanish and become negative. And there are two possible cases depending on the relative size of kappa and in X3. So here we see a somewhat richer behavior. So we have closed orbits, as we're going to see. This will correspond to quasi-periodic motion for our system. We have equilibria. Those equilibrium solutions correspond to rigid motion, meaning that the fluid domains, the measure of the fluid domains is fixed, and well, the shape of the fluid domains is fixed. And finally, we also have here a special case. Here we have homoclinic orbits. So here we'll see solutions which are asymptotically a pure rotation. Now, in the case of fluids, when kappa is 0, we see a different outcome, namely that the trajectories are no longer bounded. So here we have the generic case of unbounded solutions. All right, so what this means for our fluid domains is that they become long and thin. We have semi-bounded orbits again, and equilibrium solutions. In particular, what I've not shown here is along this axis here. This is actually a line of equilibrium solutions, all corresponding to rigid motions. All right, so let's now consider what this tells us about our full problem, the ODE system. So first, in the case where MHD case when kappa is 0, let's suppose that we're in the generic case where the function Q1 is d-periodic. The ODEs, the Hamiltonian system that I showed before, have the QIs derivatives of the QIs are periodic. Here, I mean, it should be I equal to 1, 2, and 3. I forgot to write that. So these functions here are key periodic. So if we take the average and we can change our factorization as follows, where our solution A is now the product of two rotations with constant angular velocity, and S of t is still t periodic. So here, in general, we're going to have 3 separate periods for these functions, and this is the case of quasi-periodicity. So this is the generic case for the case of MHD. Now, in this case, we have a recurrence result. If we take one of these quasi-periodic solutions, then for any integer n, we can find another integer L, which is between 1 and n squared, such that if we take L times the period t, then we return to within 1 over n of our position. So, and this is uniform in time. So it's not, of course, periodicity, but it's what we normally would call recurrence. Let's look at the case of Euler equation now. So suppose that we've got a solution of our system, in the case where kappa is 0, which is unbounded as t goes to infinity. Then we can find a couple of fixed matrices, A infinity and B infinity, such that the solution is asymptotic to this linear matrix valued function. This matrix B has rank 1, and so this tells us what we really saw before, is that the fluid domains are collapsing to a line as t goes to infinity. Now this linear matrix valued function, this state here, is not in general an element of SL2. Its determinant is expressed in terms of the 3 invariants there. However, in the case where it has determinant 1 and it belongs to SL2, then this tells us that the Lagrange multiplier is 0. And so this is the special case of 0 pressure, and our system reduces to the trivial ordinary differential equation whose solution is just a linear function. So if you remember the fact that in the case of kappa equal to 0, all solutions are geodesics, and so in particular we see that SL2 has geodesic lines. And there's an analogous statement when t approaches minus infinity. All right, finally, let's discuss the homoclinic orbit. And then I'm almost finished, so just another minute or two. In the case where kappa is 0, and we saw that from the phase diagram that there are homoclinic orbits which correspond to these conditions on the invariants. And then either we have an equilibrium solution of the phase diagram, which corresponds to a pure rotation, or the solution is asymptotic exponentially to a two-rotation solution. So notice that there are 2 different phases for this rotation depending on plus or minus infinity, and we can compute a formula for the phase shift here in terms of the solution Q1. In particular, the rotation group plays the role of a normally hyperbolic invariant manifold in this problem. In this manifold of rigid rotational solutions, we see is unstable because the homoclinic orbit acts as a unstable manifold. The thetas are constant, but they're they were the averages of the derivatives of Q2 and Q3 over one period. All right, there's an analogous result for the case of fluids. And final slide here, just so we can link back to the original PDE problem. If we go to the case of the fluids, kappa equal to 0, we see for all of our solutions that the velocity vector field is bounded. The velocity gradient, this is the spatial gradient, is bounded and actually asymptotic to a constant matrix. And the pressure is given by this formula here, where I'm just summarizing the sign of the pressure is determined by the invariance. And because of the behavior of the solution, the pressure decays to 0 uniformly in time at a rather rapid rate, and as does its spatial gradient. All right, well, that concludes my talk, and thank you all for your attention. And if anyone's interested, here's the citation for our article. So thanks very much.